So we have sine x function over x squared. When again 8x equals 100 plus minus 2 degrees. Yeah. Okay. So now your function is sine x over x squared. Yeah, it's not so easy to do the differentiation. So what you can do is you can substitute. Let's say you make a cube equals a sine x over x. Okay, then your y equals q squared, right? So now if you want to do a dy over dx, it will become dy over dq and dq over dx. Right? This is anyone remember where's the root for this one? So this is chain root, right? So okay, so dy over dq is easy, right? Dy over dq, right, is equal to 2q, right? Because y equals q squared. Okay, how about the now dq over dx now? So dq over dx basically is what? It's a d what? Sine x, right, over dx. Yeah. So again, this is what you need to do a differentiation by parts, because you have sine x and 1 over x. Okay, so what kind of differentiate result you have? You will be for sine x, right? You differentiate for sine x first, right? So this is the first one, and then you differentiate for 1 over x, right? 1 over x will give what? Minus 1 over x squared, right? So it will be sine x over x squared. Right? This is the differentiation by parts. Okay, so now if you combine these two equations, so dy over dx, right, equals dq, dy over dq, which is 2q, right? 2q is sine x over x, right? And times dq over dx, which is here, or sine x over x minus sine x over x. Right? Okay. Okay, good. Now, if you substitute in the x, right? So what is your x value you need to use? You need to use, again, you need to use the radians, not the degree. So here, sine x, you use the degree or radians, no different. Yeah, but you have x here. Right? X is your variable, right? X here you cannot use 100. Okay? You need to use the radians for 100 degrees. Okay. So x here you need to, this is in radians, right? Radians. So if you substitute in the number, you will get the dy over dx will be 4.771 times 10 to the power minus 1. Okay. I think this one you should do an exercise to check whether this result is correct, right? Okay, so now we find out what is the dy over dx. So we haven't find what is the best value for y, right? So basically this one, again, we need to substitute the x sine, so 100 degree, 100 degree is okay. Yeah. So here, you need to use radians. Yeah. So this one I show it to you how to convert the degree to radians. So basically, 100 degree, right, corresponding to pi, right? 180 degrees is pi. Right? So how do you convert 100 degree to pi? It will be 180 times pi. Yeah, right? So you need to convert your 100 degree to radians. This is square. Right? Yeah, that's the best estimate value for y. So you will get so this one you need to confirm, right? So this is my best estimate of y. Okay, so now we are ready to find out what is delta y, right? So delta y will be dy over dx times delta x, right? So this will be 4.771 times 10 to the power minus 1 times delta x. Delta x here is 2 degree. Again, you need to convert to radians. Right? So it will be 2 over 100 times pi. Yeah. So the delta of y you can get is 1.665 times 10 to the power minus 2. Okay, again, this one you need to verify whether it's correct. So the final answer will be y equals the best estimate of y will be, let's just now calculate, right? Will be 3.184 times 10 to the power minus 1, right? Then plus minus delta y, right? Which is 1.665 times 10 to the power minus 2, right? So okay, a few things here, right? So this one, the uncertainty is correct. You need to again, you need to make it as a what? As a one singular figure, right? Again, the starting point is 1, right? So what you can do is you use 1.7, right? Then the power minus 2. Then the best estimate value need to have the same order of magnitude, right? So what does it mean? It will be, it will be what? It will be 31.8 times 10 to the power minus 2, right? Or if you want to write as 0.318 plus minus 0.017. Yeah, those are correct. Yeah. Okay. Yeah. So for this part, you need to do some exercise. I think you will have for a question. So you have to do some exercise. Know how to calculate function of one variable, uncertainties of function variables. Yeah? And if you want, I can pass this solution to you. You can make a photocopy. If you want. It is the same thing as what I wrote here. Sorry? Well enough. Yeah. Well, Professor Xiao already said it. So, I mean, Okay, let's continue. Okay, how about this one? If you have function q equals to x plus y over x plus z, right? How do you calculate uncertainties? Actually, this one you know how to do, right? Basically, you need to just calculate the uncertainties for x plus y first, right? This is summation, right? And you can calculate the uncertainties for x plus z. It's also summation, right? Then you calculate x plus y over 1 x plus z. Right? Basically, now this becomes division. Right? So this one you know how to do. But the issue now here is because you have x on both sides, right? You have x on the denominator and denominator, right? So they tend to cancel each other. Okay? So this error actually requires compensating error. Right? So how do we do this? How do we do for this kind of errors? Right? So you can see if the q is a function of two variables, right? That's how we discussed. It's a function of one variable. So if it's a function of two variables, the function can be very easy. It can be q equals x plus y, or it can be very complex. For example, this one. Okay. As you can see, right, just now, even the function of one variable, right, it can be quite complex, right? Yeah. So if it's a function of two variables, this one can be even more tedious. Right? So just how we discussed the delta q for one variable function, right? So equals dq over dx times delta x. Right? So if it's a function of two variables, actually we can use the same method, right, to go from here. Right? So the result will be the delta q for the two function variables will be this one. It's very similar to the one variable. Right? This case is delta q equals delta dq over dx delta x plus dq over dy delta y. Again here, if the uncertainties in delta x and delta y are independent and random, so the sum can be replaced by the sum of quadratic. So in general, so when the q is a function of many, not only two, many parameters which have the independent and random uncertainties, right? You can always write the delta q as this one. Okay? So it's a quadratic summation of your uncertainties for each of these parameters. Okay? So yeah, this one looks a bit complex. Okay, so I think I will stop here. In the next lecture, I'm going to show you examples. Right? So